going to be a talk given in 3 series about flat bands in Moire in the first 2 parts, and then the stoichiometric compounds in the last part. And before I start, I basically wanted to say that the principles involved in this talk have been, found in a collaborative effort with basically all these researchers over the past more like 5 or 6 years. So the first row is the junior people, the second row are the senior people, and I'll be basically talking about their work here. So the 3 parts are the following. In the first part, which would have overlap with the previous 2 talks, but which will also use methods from the Kano and Neupert series that's coming, is going to be to sort of understand the single particle flat bands in twisted bilayer graphene from a sort of momentum space topological viewpoint. I think Vafek will talk about the real space picture of these bands. Then I'll talk in the second part, hopefully, about the effects of the interactions on these flat bands. And this part will have overlap with some things that you'll learn in the Vafek and Repellan talk. And the third part, I'll be talking about flat band methods, methods to basically generate flat bands beyond Moire. Sort of the Moire method is, can be interpreted as part of these methods. But these would work in stoichiometric compounds also. They're kind of a generalization of the Lieb method, and they allow us to make a catalog of flat bands in stoichiometric 3D compounds rather than just 2-dimensional compounds. Okay, so let's start. So basically, why are we interested in flat bands? Well, sort of the principle, in retrospect, kind of looking back, people were interested in flat bands because the kinetic energy is quenched and you have strong correlations. But more recently, the type of flat bands that we're interested in is turn out to be topological, for a reason that we'll go through in the third part of the talk. It turns out that there's a high probability that if you find a flat band without zero hopping integrals, or with non-zero hopping integrals, there's a high probability that it will be topological, and I'll tell you the reasons why. It turns out that almost all the topology that we've known before the flat band was sort of non-interacting. If you look at topological insulators and topological superconductors, they all kind of have an expression in terms of a quadratic Hamiltonian of fermions, and we really didn't know an example of interacting topology, with the exception of the quantum Hall, of the fractional quantum Hall effect, which is the kind of quintessential type of topologically strongly correlated state, but that requires, of course, a strong magnetic field. So we really didn't know how to marry the two, these 2 parts of physics, correlations and topology, and what would be the interesting phenomena that are coming out of a system that has both correlations and topology. So that's why we as a field, have found the discovery by Pablo so interesting, because it, in the end, in retrospect, you can also see that it kind of marries these two concepts. Okay, so topology, non-interacting topology, has been known for a while to give new types of excitations, and the excitations that we'll be talking about in today's lecture will be basically Dirac fermions. And these Dirac fermions were, of course, first seen in the remarkable discovery in graphene by Gaiman and Vasilov of single-layer graphenes. It turns out if you take a hexagonal arrangement of atoms of actually pz or s orbitals, atoms on a hexagonal lattice, and Fourier transform to momentum space, you are going to get a Brion zone, a hexagonal Brion zone that has two special points. In this case, it's got more special points. It's got the gamma point and the m point, but the special points that we'll be focusing about in this on this slide are the k points. And of course, you invariably are going to get Dirac nodes at these points if you start with s or pz orbitals sitting on the hexagonal sites. You're going to get Dirac points at the k and k prime point, and that will be explained, I guess, by Kano in her talks. But what I wanted to point out is that there's a huge amount of topology already in this very simple model. So, for example, you can ask questions like, why do the Dirac fermions show up in pairs? They always show up in pairs in k and k prime. You can ask what's keeping this degeneracy here from splitting. You can ask, why are these guys kept at the corners at the k and k prime point? Why don't they move about? And all these questions really have a symmetry answer, or a topological, should I say, answer. And you can then ask, even further questions like, what is there some characterization, some number that characterizes the Fermi surface of a Dirac fermion? And the answer to that is yes. So basically, we're just going to go very quickly through them. What keeps the Dirac nodes from splitting is a symmetry called C2 rotation by 180 degrees around the z-axis, which sends k prime into the k point, but then you act again with time reversal, and this sends it back to the k prime point, or to the k point if you started. So this is local symmetry in momentum space, and it turns out that in 2 dimensions, it protects Dirac nodes. The reason why there's 2 Dirac nodes and not 1 is called the doubling theorem that I'm sure a lot of you heard about. And this doubling theorem basically says in 3 dimensions that Weyl fermions cannot appear but in pairs. And in 2 dimensions, it says that Dirac fermions, which are protected by this symmetry, can then not appear but in pairs. And so that's a doubling theorem. Then what's holding these Dirac fermions at the corner? Well, that's C3 symmetry. If you break C3 symmetry, you'd be able to move them about. But still, this C2Z, the C2 times T symmetry would locally protect the Dirac fermions. So what I'm trying to point out here is there's a huge amount of symmetry arguments that basically can explain this universal property that if you put s or pz orbitals on a hexagonal lattice, you're going to get Dirac fermions. Now, what's a way to kill this doubling theorem that you have in 2 dimensions? Well, topological insulators actually do that. And you can sort of understand topological insulators as taking one of these Dirac cones and moving on the upper surface of a 3-dimensional sample, and taking the other one of these Dirac cones and moving them on the lower dimension, on the lower surface of a 3-dimensional sample. And you can, of course, as I said, not do that in purely 2 dimensions because there's a doubling theorem, but you can do that in 3 dimensions. Okay, so I hope I convinced you that there's a huge amount of symmetry here. So how do we do to marry sort of topology and interactions? Well, the simplest way in retrospect, so again, these are all retrospective comments, is to basically take a system that's got topology, such as graphene, which has got these Dirac nodes, and which alone doesn't do a lot of interacting things. It does some, but not a lot of them, because the density of states is very small at the Dirac point, and sort of do something to its bandwidth, which is electron volts, to make the bandwidth as small or smaller than the interactions. Okay, and this brings us to basically a new scale in the physics of these systems. By the way, please, I'm not sure how it works, if you can interrupt while the talk is going, but and I'm not sure what the policy is, but well, I guess do they told you in the policy, but I don't mind if you interrupt me while the talk is going. Okay, so as I said, you know, making these samples where the interactions are kind of competitive with the hopping requires going to a different length scale. And why is that? Well, if you take material chemistry, which has an inherent scale, stoichiometric materials have inherent scales of few angstroms, generically, you will get hopping integrals or bandwidth of order electron volts. And I'll show you in the last part of the talk that for special systems, then you can kind of go through high throughput and find them. That's not true, but generically it is true in the sense that, you know, for 90% of the cases or 95% of the cases, or it's true. Now, there's another length scale, which is that of optical lattices, which is much larger than the graphene lattice. And this is the cold atoms optical lattices scale, in which this length scale about a micron. But in between them, there's this length scale that, you know, people like Emmanuel Tutuk and Pablo and others have exploited in the past, which is the Moire superlattice scale, which basically is of the order nanometer scales. And this is really a way to get flat bands or a high density of states from still crystalline materials by doing a little bit of engineering with them. Okay, so here what you have is an example of such a Moire lattice under different deformations. So this was, you know, some version of this was showed in the previous talks, but basically what you do is you take a layer of graphene, you put another layer of graphene on top of it, and then you twist it by a small angle. But you can do more than that. You can, you know, twist it, you can strain it, you can strain it in different directions, you can compress it, you can slide it, etc. And all these things, for example, create deformations of the lattice, and, you know, you can write a small Mathematica code that gives you exactly how the lattice deforms and how a superstructure arises from these deformations. Okay, so the interesting thing, of course, was that when this was done in Pablo's group, they found an amazing array of interacting states here that we're going to get to. But first, let's kind of understand what happens when you take two layers of graphene and twist them with respect to each other. Of course, this is kind of a review of what was shown in the previous talks, but we'll take a different angle in the next slides. So very shortly, and this, you know, you can find this explanation very clearly in these papers. What happens is that we know where the physics of the lower layer of graphene and the physics of the upper layer of graphene happens. The physics of the lower layer of graphene happens around the points, you know, K1 and KY1 prime. So we call one layer the layer 1 and the other layer the layer 2. Okay, so this is where you have a Dirac fermion in the lower layer, and this is where you have the other Dirac fermion that I said is necessary by lattice doubling in the other layer. Now, when you add in the same layer, but in the other valley. Now, in the other layer, you also have a K point with a Dirac fermion and a K prime point with another Dirac fermion. So now you have, of course, two Dirac fermions per layer, 2 layers. You have 4 Dirac fermions. But what turns out to be the case is that if this angle is small, if the angle between the two twisted layers is small, then you have a phenomenon which is basically called valley decoupling, which means that if you couple these layers, if you couple layer 1 with layer 2 through hopping integrals, so this so far is just single particle physics, if you couple them with hopping integrals, what will happen is that you're going to create a small, you know, called Moire-Briand zone, which is a new periodicity, this large periodicity in space, the new periodicity. And here is exaggerated because this angle here, here is probably 10 degrees or 12 degrees drawn, but in reality it's 10 degrees, it's 1 degree. So it's much smaller than this. You just can't see it if I would draw it like this. Okay, and basically what happens is that the probability of tunneling between the physics given by the Dirac fermions at K of the lower layer and K of the upper layer, and the Dirac fermions at K prime of the lower layer and K prime of the upper layer, so doing this, is kind of proportional to, there's some path factor which I won't give it, it's kind of proportional to the interlayer coupling, W, over the intralayer hopping to the distance between the K points, so K minus K prime, over the distance between the small K points, which we call Moire. So this distance here is just this distance, is this distance. And this distance here is basically this distance, okay? And this just comes out from perturbation theory. In order to couple these values, you need to basically tile this Briand zone perturbatively an amount of times to get to the other K point. Now, this is a large number. It's of the order, this number is of the order 1 over theta. W is smaller. W is the interlayer hopping. It's smaller than the intralayer hopping by factors of 10. So this is an exponentially suppressed number. So what happens is that you have a valid degree of freedom, and this valid degree of freedom basically tells you that you can look at the physics of the system of this twisted layer as the physics around one valley, which comes from the K point of the upper layer and the K point of the lower layer, and of graphene, and decoupled in the non-interacting case. They'll couple interactively with interactions. Decouple the physics from the other valley K prime. Okay, so let's look at the physics within one valley. As we said, you have, this is the K point of the layer 1, and this is the K point of the layer 2. Okay, and if the interlayer hopping is much smaller than this distance, this energy scale, okay, which is this energy scale is basically the Fermi velocity of the Dirac fermion times K theta is basically this momentum difference, is the small Moire-Briand zone momentum difference. If it's smaller than this, then you basically just have two Dirac cones, one on top of the other. Nothing very interesting happens. However, this is tunable, this K theta, because K theta is proportional to theta, okay? And it's tunable in such a way that you can make theta small, and hence you can tune it so that you have the following condition, that the inter-layer hopping is basically of the same order of magnitude, or equal to the Fermi velocity of the Dirac fermion times this momentum difference, which is basically, this momentum difference is basically the characteristic length scale of the Moire-Briand zone, okay? Or the characteristic momentum scale of the Moire-Briand zone. And then what happens is that invariably this difference becomes important, and you have a manifold. You have basically the Dirac nodes flattening their velocity, okay? You have this doing this and getting less and less dispersive, and at the end, the Dirac nodes have flattened their velocity, and you get flat bands. Now, there's a further, more subtle flattening that even at small angles, some angles are special, and these are called as magic angles, which you'd need to go through the approximations of the model to fully understand them, but I'll give you a more generic picture in terms of line graph lattices. Later, it turns out that you can write the graphene tie binding, you can write a graphene tie binding model if you neglect some symmetries, a twisted bilayer graphene tie binding model if you neglect one particular symmetry called particle hole, which basically makes it so that you have exact flat bands and the system is, and the model is a line graph, which I'll come back to later. Okay, so we argued that small angle should have flat bands, or bands that are flatter than, much flatter than the original bands. But how flat are they? Well, if you look here, you can see these plots which were already shown in the previous talks. You can see these plots. These are some plots at, for example, I guess this plot includes relaxation, which is just from this paper by Koshino et al. And these bands are basically incredibly flat compared to the other bands, and we call these the active bands. These will be called active. Okay, and how many active bands are there? Well, there's a bunch of them. There's actually 8 active bands. And why are they 8? Well, you have, as I said, 2 spins. So there's a spin degeneracy. You consider low spin orbit coupling, and you have 2 valleys. So as I said, the physics around K decouples from the physics around K prime of the original graphene. Notice that these are the K of the Moire lattice. So they're the different Ks. For example, these are the Ks of the Moire lattice here. This is K Moire, and this is K Moire prime, okay? And K Moire is, for example, the K of the upper, or K prime of the upper layer, and the K Moire prime is the K prime of the lower layer, etc. Okay, so again, you have a factor of 2 from spin, you have a factor of 2 from valley, and then you know that your bands come from Dirac fermions. So there's another 2 because the Dirac fermion has 2 states. So that's 8 bands in total. And that means that as you go from a gap, from a single particle gap that's here, in this gap, filling that's here, to a single particle gap that's here, you have to add 8 electrons in between these two to, there's differences of 8 electrons per Moire unit cell to go in between these two. Now, the Moire unit cell is very large, so 8 electrons per unit cell is not a huge density, and you can actually tune it, as was shown by Pablo. You can actually tune it, and you can get between this gap and this gap by just gating the system. Now, what we'll be talking about in this talk and in the other parts of the talk is the electron filling of the flat band relative to charge neutrality. So this would actually then mean charge neutrality is in the middle. So this would mean, this gap would mean -4 electrons per unit cell. And this gap here would mean 4 electrons per unit cell. Okay, and that's kind of like the accepted theory talk that you'll find in a lot of the papers in this system. Okay, so now let's go a little bit deeper into this, into the physics of these bands. And that's done, as was shown in the previous cases, by McDonald and Bistritzer. This is called the Bistritzer-McDonald model. And this model is, it's not, you need to work a little bit to get it, but in principle, you can argue it. And certainly the topology of the bands that I'll teach you about, you can argue it sort of model-free almost, with some constraints. But basically, the Bistritzer-McDonald model is a model that takes, it's a model for these flat bands. So it's a model that basically takes the Dirac fermion of, it's a model per valley. So this is around the valley K, which means it uses only states at the K point of the lower layer and at the K point of the upper layer. Okay, there's a model at valley K prime, which uses states from K prime of the upper layer and K prime of the lower layer. So the model around K contains, this is the Dirac fermion of the upper layer. This is the Dirac fermion of the lower layer. And here you can see that I've made an approximation. Normally this derivative here there should be a rotation because the upper layer is rotated by the lower layer. Usually in most theoretical models, although not in all, people basically just take this model because the change by putting a rotation by theta when theta is small is very, very small to these diagonal terms. And fundamentally, a interlayer hopping, which is T of R, which is modulated at the Moire length scale. So this T of R has modulations over the Moire length scale, which are 10, which is 10 nanometers, so roughly of the order at theta equals to 1. And this has a particular expression. These factors, e to the IQR, are the ones that create the modulation, and the small q's are basically the difference between the K point of the lower layer, and this is the K point of the upper layer, which are actually just become the Moire K prime, Km prime point, and the Moire Km point. Okay. So this is what they become. And up to a gauge transformation, this interlayer hopping is modulated at a length scale, which is the Moire unit cell. Now, these two numbers are called AA coupling, and this is AB coupling, okay? AB regions coupling. And the reason why they're called so is because you notice that there's here this sigma in the Dirac Hamiltonian acts on the AB sublattice of the graphene, and this W0 is diagonal in that lattice, so that's AA, and this W1 is off diagonal, so that's AB. Okay, so it's a model that has two parameters, W0 and W1, and really what will be important is, what will be very important is their ratio. Okay. Okay, so how do you solve that model? Well, one way to solve it is to go to momentum space, okay? And to go to momentum space is, instead of, you have your Fourier transform this, how does it, let's see. Okay, you Fourier transform this guy, and you see that you're gonna have a lot of plane waves, okay? You're gonna have scattering between a lot of plane waves. And for example, this is, if I keep the momentum K in the first Moire-Briand zone, so momentum K stays in this region, then the T of R will basically give you scattering between, this point and this point, this point and this point, because of the e to the IQR, okay, small q. These small q's are just these guys. So then this model now in momentum space is solved on a big lattice. Is actually numerically, analytically the lattice is infinite. Numerically you only need basically 3 or 4 shells to get to machine precision. So numerically, if I solve the model at angle 1 on this is momentum space lattice by taking a lot of this many plane waves, then I already get to machine precision. And you can just diagonalize your model on this momentum lattice with K belonging to the first Moire-Briand zone, and then you have the next Moire-Briand zones by taking further and further plane waves. Okay, so now what we want to ask is, given that model, we want to take the route of trying to obtain kind of model independent statements and ask, we know that model has flat bands because we can solve it. Mr. McDonald did that for us. We know it has flat bands. So we want to ask, what topology, if any, do the flat bands have? And again, as I stress, it will turn out that the flat bands are topological. I'll give you a reason for it now. And it actually turns out that you test a lot of these models that have flat bands that are not atomic. Well, then I'll tell you what that means later, but basically it means that the hopping integrals are non-zero. So the flat bands don't come from having zero hopping integrals. The flat bands come from having non-zero hopping integrals, but have some interference. And you find out that a lot of them, there's not all of them, we find out a lot of them are topological. So there's got to be a reason for that, and that's the reason that we'll learn in the third part of the talk. But so far, I want to basically analyze the previous model with respect to the symmetries. So I'm going to talk about the Bistritzer-McDonald models as a set of models, not just this particular model, a set of models that comes basically from taking the low energy physics of two layers and coupling them with a Moire potential. Okay, so this for if the two layers are graphene, then and if the system keeps the symmetries that you had in the single layer, but with the extra fact that you have now a good Valley quantum number, then you are left for the twisted Moire model around the K point with the following symmetries. So C3Z is a good symmetry, and C3Z basically is a good symmetry because it takes the K point of the lower layer and the K prime point of the the K point of the lower layer and the K point of the upper layer, or the K point, the K Moire point, and the K prime Moire point of one valley. It takes them to the C3 times K and times K lower and C3 times K of the upper layer. And these are related to these by a reciprocal lattice vector in the original small unit cell graphene lattice. So they're basically the same points. So then if I do the physics around here, I still have C3 as a good symmetry. Okay, so C3 is a good symmetry, and this is what this symmetry does to the plane waves, to these small Q vectors that form the plane wave lattice. This is K Moire, this is K Moire prime, okay, etc. So this is what the symmetry does to this. It switches one into the other, okay. And then you have C2X, which is also a good symmetry, okay, of the single valley Moire system. And C2X basically is 180-degree rotation around the x-axis and takes the K Moire into the K Moire prime point. Okay, that's what this symmetry does. Notice that it left, okay, the K point of the original graphene lattice invariant. Well, it switched it into the K point of the upper layer, but it left the valley invariant, and that's why it's a symmetry of the single valley Bistritzer-McDonald model, the valley around the K point of the upper layer and the K point of the lower layer. And now you have the extra symmetry that's actually the most important in this system, which is C2 times Z symmetry. And this symmetry does the following. Okay, on a single layer graphene, okay, on a single layer graphene, C2Z times T, C2Z takes the K point into the K prime point, and T sends it back. So this is a symmetry that, again, doesn't change momentum. It's the same symmetry that keeps the Dirac points invariant in single layer graphene. And it's going to be the same symmetry that keeps the Dirac points invariant in the double layer graphene, in the twisted, two-layer twisted graphene. Okay. So this symmetry, since it keeps the momentum, doesn't change momentum, is a good symmetry of the Moire system. Notice that just time reversal by itself is not a good symmetry of the valley, of this one valley model. Why? Because time reversal by itself, even though it is a symmetry of the full system with two valleys, so you have this one, and then you have a rotated this is the original graphene Brillouin zone. Time reversal sends the K point into the K prime point. So if your physics in a single value uses states only around the K point of the upper layer and the lower layer, then time reversal would change it to the physics of the K points of the K prime points in the upper and the lower layer, and hence time reversal is not a good symmetry of the single layer of the single valley Moire system. Okay, there's a question. Okay, so this is very good. There was a question, why do we need to use a magnetic point group for a non-magnetic system? It's a very good question, and this is what I'm coming to. So, as I said, if you take into account two values, then the physics stays time reversal invariant, okay? So this time reversal sends one valley into the other valley, okay? However, if you want to use the fact that you now have a valley symmetry, so basically if you want to use the full extent of your symmetries, the fact that you have a valley symmetry, which would actually be a large symmetry. It's will give you a continuous symmetry. If you want to use that, then around a single valley, okay, the physics doesn't have time reversal because time reversal switches to the other valley. So if you want to filter the valley quantum number, then the symmetry group is magnetic, is not a non-magnetic symmetry group, even though the material is in the single particle formalism, still non-magnetic, etc. So that's why you need to use a magnetic space group, okay, for figuring out the physics of the single valley filter system. I mean, it's not necessary, but it makes things a lot more transparent. Okay, I hope that answers the question. If I was to find a symmetry group for the two valleys together, it would be a non-magnetic space group, but that would miss the fact that in single particle, these states at valley K do not couple to the states at valley K prime, okay? And the price you have to pay for just using the valley K model is you lose time reversal, but this is not essential here. You recover it by going to the other valley, and it's much easier to see the topology per valley because it's a good quantum number. Okay, so then fundamentally, so I hope that answers your question. If it doesn't answer, write another question, please. Okay, so another symmetry that's actually very important basically backtracks from the following symmetry of the Dirac fermion. So in single layer graphene, the Dirac Hamiltonian is K, okay, just K dot sigma, okay. This is with some velocity, which I picked to be 1 here. This is h of k, okay? And you can see that h of k is equal to trivially minus h of minus k, okay? Just from its form. This is an approximation. It's an approximation, however, to very good accuracy. And h of k around the Dirac point is equal to minus h of minus k. Notice that this is a unitary particle hole, okay? Why? Well, particle hole, so unitary particle hole. Particle hole, what particle hole would do is send k to minus k, flip the Hamiltonian, and transpose it. Okay, this doesn't have the transpose. Okay, so particle hole is usually anti-unitary. This doesn't have the transpose. It's a unitary particle hole symmetry because it changes. And this basically backtracks into the two-layer having the same symmetry per valley, actually. So notice that this is the Dirac Hamiltonian single layer graphene around one valley.
Andrei, okay. You have another question.
Okay, sorry. Is the time reversal shown for spin-full or spinless? Very good question. Spinless. You neglect spin-orbit coupling. It's a effect of less than 0.1% here. So I'll come to talk about spin-orbit coupling afterwards in a little bit. But yes, very good question. Both questions very good. Spinless time reversal. So just complex conjugation for time reversal. Okay, so you have particle hole symmetry. Okay, and this particle hole symmetry is actually a little bit weird in the sense that normally particle symmetry commutes with all your, the particle symmetry that you find in the topological superconductors, etc., commutes with all your spatial symmetries. Here, it actually turns out it anti-commutes with C2x. Okay, so it anti-commutes with this symmetry with C2x. And, we can get into the reasons for that. The reasons are actually, they all come, you can understand the reasons by looking at the single particle of the single layer and kind of mixing, putting them together to form the two layer, but it all backtracks from the particle hole of a single layer. Okay, so C3Z, C2X, C2Z times T, and particle hole. These are the symmetries. Now what we want to do, as you learn, so I don't have time to go on to the reason why really you want to do this, but you learn this in the Kahneman and Neupert talks. But what you want to do, once you have a symmetry immediately, is to look at how the bands transform on the symmetry. And these are some generic statements about symmetries, about these particular symmetries. So for C3 symmetry, there's 3 one-dimensional irreducible representations, and they have these eigenvalues. Okay, that's pretty clear because C3 cubed has to be equal to 1, again, for the question, spinless systems. The spin is just a multiplication by 2. Now, if you add C2Z times T to this system, then these 2 one-dimensional representations of C3, okay, which are complex, they basically become a 2-dimensional irreducible representation, because C2Z times T, this time reverse, which is complex conjugation, flips I, so switches this one into this one, and makes the representation 2-dimensional. Now, of course, you know what this 2-dimensional representation is. It's just the Dirac node. This is the 2-dimensional representation. This is the reason why, part of the reason why you have a Dirac node. Okay. Then, what are the eigenvalues C2x? Where C2x squared is 1. Squares to 1 for spinless systems. So the eigenvalues are 1 and -1, the characters of the irreducible representations. So now let's add particle hole into this mix. Particle hole, the particle hole that we had before, commutes with C3 and anti-commutes with C2x. Okay, so what does this tell you? Well, this tells you that if I have a state at energy E non-zero and a state of energy E minus E, because particle hole flips the Hamiltonian to energy minus E at minus K, but consider Ks that are invariant under K to minus K, then if this has an eigenvalue C3, this one will also have an eigenvalue C3 because P commutes with it. However, if this has an eigenvalue C2, X being 1 or -1, this guy will have to have an eigenvalue minus C2X at minus E. Why? Because, of course, P anti-commutes with this, so you get another minus sign. Okay, so now embarked with that knowledge, let's find out the symmetries of the bands at the high symmetry points. Okay, the symmetries of the bands at the high symmetry points invariably of details of the model. So now I'm not using any specific model. And what I claim is that if you take a model with all the symmetries that you have per valley, okay, so C3, C2x, C3z, C2x, C2z times T, and particle hole. If you take a model with these 3 symmetries and assume, this is per valley, so assume the angle theta is small, then the representations of the lowest 2 bands, so the bands, the first band above charge neutrality and the first band below charge neutrality, are fixed up to some permutation. So let's find out how that is. Okay, well, that's very simple. Okay, let's see, it's another 2 questions. I don't really understand why particle hole symmetry has to be included. It doesn't have to be, but I'm including it for the reason to make a model independent statement. Then I can relax it if I want to. Okay, that's the first question. Since magnetic groups have many unitary operations, are we missing any anti-unitary ones? And we're not missing any anti-unitary one. Those are the generators of the group. So those are the generators. You can of course form new symmetry operators by taking generators and multiplying them around. Very good questions. Thank you. So, okay. Yeah, so if you want some other symmetry, some other non-unitary, you just multiply the C2ZT non-unitary with the other unitaries. Very good questions. Okay, so now let's go to the following. Let's go to this argument. So you take the coupling between layers to be alpha, and this alpha coupling you can tune it from 0, okay, where the two layers are uncoupled, to all the way to the value, whatever the W0 and W1 values of the interlayer coupling. Okay, I want to make this experiment where I tune this. Okay, and let's see what stays constant in between these. Okay, well, at alpha equals to 0, so I just had the lower layer and the upper layer, the representations at the Moire K point are fixed. We know that there's a Dirac node at the Moire K point. There's another one at the Moire K prime point. And we know that it's got representations e to the I 2 pi over 3, okay, plus or minus these two, okay, plus minus these two states have this represented. These are the Dirac nodes. You can get the representations from the single layer graphing. They have this representation on the C3. They're fixed. Now, what you know is here, first of all, that if you change alpha, if you make alpha to go from 0 to the interlayer coupling, these representations have to be stuck at 0 energy. They cannot move. Why can they not move? Well, if you have particle Hall, if they moved, you know that if I had a representation K2 here, which would be the plus in e to the plus 2 pi I over 3, you know that if I had a plus, the K2 representation here, if they moved, and here would be the plus in e to the I plus 2 pi over 3, since particle Hall commute with C3, here it would also have to be plus, okay? And not minus, whereas the K2, for example, is the plus, and the K3 is the minus, okay? So there's no particle Hall way of moving them away from 0 energy, or of moving a doublet, for example, away from 0 energy. If this moved all the way up here, you know, if I had them doublet here, particle will tell me I have to have a doublet here, so it would mean I have 4 states, not just 2 states. Okay, so what we've learned is that no matter what I do in this process of taking 2 layers and ramping up their coupling, the representation has to be a Dirac point here, K2, K3. Then, by the same token, because particle Hall anti-commutes C2x, okay, you can find that the representation at the gamma point and at the M point, which are invariant under C2x, these are the points invariant under C2x, they have to have opposite inversion for opposite C2x eigenvalues, okay, because as we said, this flips the eigenvalue, okay. Whether this is gamma 1, you can find it here has C2x eigenvalue 1, and gamma 2 has C2x eigenvalue -1. Whether this is gamma 1 or gamma 2, or whether this is gamma 2 and gamma 1, they can flip. But the fact is, if one is gamma 1, then the other one is gamma 2. Okay, so that means that if I have 2 bands around you know, the charge neutrality point, and these 2 bands are gapped from all the other, you know, bands, so these are the active bands of the twisted bilayer, I know the representations, okay, up to this switching around, okay? So if I know the representations, what I can do, and this will, Kano and Neupert will, you know, refer to aspects of this. I think it'll be an integral part of the Kano talks. What you can do is you can, you know, put the representations in a table, Okay, this is the lowest set of bands of the twisted bilayer. And as I said, there's a gamma 1 representation and gamma 2 at the gamma point, and they're both one-dimensional. There's a K2, K3 at the K point, and there's an M1 and M2 at the M point. Okay, so you can put them in a table, and then you can go on this website that part of the people that I showed on the first slide build the theory and behind it and the website, etc. Okay, you can go on this website and you can go to this symmetry group, to the symmetry group of twisted bilayer single valley, and find its atomic limits, meaning you can find the eigenvalues. There's a machinery, there's a basically just machinery that churns out, given any orbitals, any localized orbitals on the lattice, it gives you the eigenvalues of these bands of the bands formed by these orbitals at the high symmetry points. Okay, so then you can go and there's a finite set of them. You can find them all on this server. They're called, basically elementary band representations. They're tabulated for every group. And if you have this set of lowest bands in graphing, you can immediately see, even by eye inspection, but there's a code given on this website of how to do it without eye inspection. But the thing you can see clearly by eye inspection here, that you cannot write these bands in terms of sums of atomic bands. So for example, if I had these atomic bands, these would be from, S and P orbitals at sitting at the center of the hexagonal lattice. So I'm asking, can I write these bands as sum of S and P orbitals sitting at the center of the hexagonal lattice? And the answer is no. Why? Because the gamma eigenvalues would match, an S and a P orbital sitting at the center of the hexagonal Moire lattice would give you a gamma 1 plus a gamma 2. It would match, the M point would match, but the K point would not match. You can see that it would give you two K1 representations, whereas in reality you have a K2, K3 representation. And you can go through this exercise and convince yourself that there's no way that you can write down the twisted bilayer bands as sums of what's called elementary band representations, or i.e. atomic limit, localized atomic limit. So basically that tells you immediately that the twisted bilayer active bands are topological. And it also tells you that if you keep particle Hall, all the symmetries, particle Hall, C2, CT, and C3, etc., they are topological at any angle, any small angle. So as long as I made a small angle of twisted bilayer so that I have this valley decoupling, and as long as I have two bands disconnected around charge neutrality, disconnected from the other bands, now of course they could have gapless points to the other passive band, then the system is going to be, then these two bands are going to be topological. So this is a very strong statement, basically stating that the lowest two bands in twisted bilayer are always topological. Now, what I want to do is find out, what we want to do is find out what type of topology do they have. And in order to do this, what you take is what's called the Berry phase calculation, where you basically take these two bands, compute their Berry phase, their non-abelian Berry phase, which is also called Wilson loop. So the Berry potential is a matrix, and you kind of take a path-ordered integral around one direction, and you plot it as a function of momentum in the other direction. Okay. Normally, this, I mean, not normally, basically in every case, generically, this is not approved, but in any case that we tried, that anybody has tried to see whether these Wilson loops reveal the topology of the system, the answer has been yes. Okay, so for example, if you have a churn band, a single band, then the eigenvalues of this Wilson loop will basically wind. So this is a unitary operator who's got eigenvalues between 0 and 2 pi. They would wind as I move this momentum, okay? As I move this momentum, as I plot the eigenvalues versus this momentum. So I take the Wilson loop, or the integral of the Berry potential in this direction, plotted versus this direction here, they wind. For a quantum spin Hall system, where I have 2 bands at least, you'll see, the time reversal winding of the Vanier centers. These are 2 time reversal one Vanier center. This is a Kramer's Journey. This is a Kramer's Journey, etc. Okay. So what you do is you take this for twisted bilayer and you do this, and in the regions where 2 bands are gapped from the other bands, the 2 active bands are gapped from the other bands, you get something that's basically topologically equivalent as winding to this. I'm going to go on for like 3 more minutes and then finish. It's topologically equivalent to this. You can see that they're basically more or less the same with some different, some wiggles around it, but you have a center that winds in one direction and a center that winds in the other direction. So basically kind of like a spin up in magnetic field up, spin down, magnetic field down. So this looks very similar to this, to the quantum spin Hall, okay? But the symmetries are very different. One symmetry is time reversal, spinful time reversal for quantum spin Hall. One symmetry is spinless time reversal, C2Z times T, okay? So even though the Wilson loop looks the same, actually the Wilson eigenstates, the eigenstates of the Wilson loop are very different. And it was long thought that the topology of these bands would be what's called fragile, meaning the following thing. So whereas in a topological insulator, so the winding of the Wilson loop, I'll answer the question when I finish here. So whereas the winding in the Wilson loop of a topological insulator, these with time reversal, with spinful time reversal, these points are protected by Kramer's degeneracy, and adding bands to the system, with Kramer's degeneracy would give you a Z2 classification. Here, adding bands to the system can make these 2 states trivial. That's not true if you keep all the symmetries, as I'll show you in a little bit. But basically, this is kind of like at the beginning, this was thought to be true. So if I have, these are the 2 active bands, okay? These crossings turn out to be protected not by time reversal, because I don't have time reversal in the single layer system, but by C2 times time reversal, okay? These crossings are protected by C2 times time reversal, and this crossing also. So they're locally stable. They can move around, but they're locally stable. But what I can do is add 2 more bands to the system. So I add 2 more, say 2 more trivial bands, just simple orbitals, just to stake and add 2 more simple trivial bands, and now do the Wilson calculation of the full 4 bands of the system. And it turns out that these crossings here are not protected, okay? That actually turns out, so they're not protected, so they can open a gap here, and then you can have no winding. So you can have a Wilson loop of 4 bands, which basically does something like this. And I think, as Neuper will point out from the abstract of his talks, this basically means no winding or no topology. So this means that the state, which was 2-band topological, when you add bands, when you add 2 bands, it can become trivial, okay? So this is the concept of fragile topology, and basically it tells you that if you add trivial Hilbert spaces to a non-trivial fragile topological problem, it can become trivial, okay? Now, I wanted to end with this slide. It turns out that actually, if you keep particle Hall symmetry, and this is the reason why I'm answering the question, why would you want to keep particle Hall symmetry? So this winding here of the 2 bands is all you need. Is you don't even need the crystalline symmetries. All you need for the winding of these 2 bands for making this classification is C2Z times T, okay? That's the only symmetry that you need, which basically protects these nodes in the Wilson loop. But what's usually beneficial is to use the full symmetry of the system and then ask, if I kill X, Y, and Z symmetries, okay, do I still have topology, or does the topology change? Okay, and it turns out that with particle Hall, if you maintain particle Hall, the topology is actually stable, not fragile. So this is something that I'll go through next time. But basically, there are several statements that I wanted to make. Statement number one is that particle hole is actually good at low energies, and it provides stable topology. So in other words, the TBG in one valley is topologically anomalous for any number of bands. This is okay because you have a continuum model. You couldn't have this in a tight binding model, okay? Because time binding model has a bandwidth, and then if you took all the states in that bandwidth, all the bands together in a tight binding model have to be trivial because they're just the orbitals of the tight binding lattice. But here you have a continuum model, and in this continuum model, there's no contradiction to all the bands being topological. For example, one continuum model where all the bands are topological is the surface of a three-dimensional topological insulator. On the surface of a three-dimensional topological insulator, no matter how many bands you take, all of them are topological. Now here, the interesting thing, so the surface of a topological insulator is anomalous. Now here, the interesting thing is that you have a two-dimensional model by itself that's anomalous. The difference is that it's a continuum model around one valley. If I took the other valley and added it in, it wouldn't be anomalous anymore. Okay, so I'll show you how that happens next time. And now I finish and take questions. Thank you. I actually cannot read the questions. Let's see. Oh, hang on 1 second. Okay.
I can read the questions.
Oh, I can read them too now. I just had like a technologically challenged moment. Okay, I can read the questions. So question number one, can the lowest graphene band, so again, lowest means the ones around charge neutrality. So said by particle hole come from one branch of disconnected EBR or not? That's a good question. I would assume yes. Yes, I think yes. They can be a disconnected branch of an EBR. I think that's true. I think that's true, but don't quote me. In any case, you can go and check it immediately on the Bilbao crystallographic server. All for the symmetry group, all the EBRs are tabulated, and I think you're right. The answer is yes. Okay, next question. Does the EBR decomposition capture the weak nature of the TI? So this is, so it's a fragile nature. So first of all, the fact that here you don't have, let's see what it is. So the fact that there's no way you can write down these eigenvalues as compositions of elementary band representations, i.e. atomic limits, or also known as atomic limits, immediately shows you that it's topological. Now, if you squint and are kind of like very quick to notice, more quick than I am, you'll see that you can write this down as not sums of atomic bands, but sums and differences. Okay, so that basically tells you that it's not strong topological. Now, all these, so I kind of said then afterwards, I said, oh, but with particle it's topological. So why does it's strong topological at all bandwidths? So why don't they show up in this? Well, the Bilbao crystallographic server doesn't contain particle hole because particle hole is not a crystallographic symmetry. Particle hole is kind of a symmetry at low energies. It comes from the low-lying excitations of the Dirac fermions, and it's certainly not included as a crystallographic symmetry. It's included in an effective symmetry. Not being included in the crystallographic symmetry, this is outside of the theory, that Barry, Jen, Luis, Maya, and Zijun made. So basically, it wouldn't show up in these cases if you have extra symmetries like particle Hall, you'd have to add them up afterwards. So, but that's good because that means you can find new stuff. Okay. I hope that was answered. Next question, can this be generalized to other systems with crossing, not necessarily Dirac at any point in the Briand zone? Yeah, it's a very good question. So can this type of argument be generalized to other systems? So for example, to other Moire systems. So the answer, the full answer is I don't know. It's certainly a very good question. One could, possibly do it on the square lattice with some symmetries, which has a Dirac node at the corner. You can do a similar situation. The special thing here is that, if I just had C2Z symmetry, I would have fragile states. And, in order to see that they're topological, I would have to compute their Wilson loop. Here, I can just do it from just eigenvalues because I have these rules for how the eigenvalues of the bands work. So I guess you could do a similar thing if your system has eigenvalues and if your excitations are that you start off are relatively easy, like a Dirac node, etc. If you start off with a large Fermi surface and then put 2 layers and twist, that becomes much more complicated because you have a lot of states. But if you just have a Dirac point like here, the crucial thing about these arguments was the fact that I could go away from zero coupling between layers to non-zero coupling. So I think, Inigo, that's the answer to your question is that this is basically a research question. So I think it should be possible. And I think it would be very interesting to find out if it's possible to do it for other lattices. The downside of it is that, not many people will care unless these lattices are experimentally foundable. So pick a lattice that, people can do this twisting on. That's a very interesting question that should be answered. Okay. Does this fragile topology have quantum spin Hall effect? So it doesn't have quantum spin Hall effect in the sense of having edge states. Okay. So why is that? So I think Titus will, maybe Jen will talk about this. Certainly Titus from his abstract. Really the symmetry that protects this, I can kill all the symmetries, and this fragile topology in the end is protected by just C2Z times T. I can kill all the other symmetries and I'll still have a protected state, okay, as long as I keep C2Z times T. Now, what's the difference between C2Z times T and just T? Well, first of all, for the quantum spin Hall effect, T for the quantum spin Hall effect is squares to -1, C2ZT for this case squares to 1, but that's one of the differences. The difference physically is that the time reversal for the quantum spin Hall effect keeps the edge invariant. Okay, so it's a local symmetry. So if I cut the sample and make an edge, then time reversal acts locally on the edge. Okay, so it has edge states. It's topological state going to the back of the edge states. Now, C2Z times time reversal, if I make an edge, C2Z flips this edge to this edge. Okay, so C2Z, so the symmetry that protects the bulk being C2Z times T, once you make an edge, it flips one edge into the other. So an edge breaks locally C2Z times T symmetry. So you wouldn't expect edge states, and there's no edge states. But what there are corner states, as Titus will speak about. So basically, these two edge states, if I, for example, take a quantum spin Hall with C2Z and T squared equals to 1, then kill both C2Z and T, but keep C2Z times T, this edge would be mapped into this edge, and then at their intersection, kind of like a rhombohedra here at the intersection, you'd have corner states. So this is, some sort of a higher order a topological system, as most fragile states are. Okay. Last question, I guess. I believe that, okay, not last question. I believe the Fredholm models are used to describe topological properties in TBG, and they obtain reasonable predictions related to topological properties in TBG, such as Chern states. Okay, so that's a comment, not a question. Okay, yes, I mean, the business of McDonald model is used to make predictions, and that has stable topology because it's got particle Hall. Okay, so there was a comment. Can you say something about what happens when you couple K and K prime? Does it trivialize the bands? Yes, it does trivialize the bands, but what you have to remember is that the coupling between K and K prime is exponentially, vanishingly small. There's some issue with the number of paths you can take, but in the end, it turns out that the coupling is exponentially small. Okay, so the coupling being exponentially small, if you add K and K prime, you trivialize the bands, but by an exponentially small amount. Okay, so you basically don't trivialize them. I mean, if I'm, if you were to couple them and add a significant term between them, then you trivialize them. But basically, because the coupling is very small physically, the trivialization, which would be measured by, if you'd couple K and K prime, you'd get twice this, and then you'd get a small gap here in the Wilson loop. But this gap would be vanishingly small, exponentially small. So really, you wouldn't get a trivialization. Okay, unless you add strong coupling between K and K prime, which is not physical. Okay, does it make sense? Any more questions?
Yes.
There's more questions. Okay, can you interpret the higher topology from the Wilson loop spectrum? Yes, you can certainly interpret it from the Wilson loop spectrum if you know the symmetry that protects the Wilson loop spectrum. So if I showed you just the Wilson loop spectrum, if I showed you just this, okay, so say you come to me and you say, oh, well, show me the Wilson loop, and I just showed you this, you wouldn't be able to distinguish it from this if you just saw the Wilson loop spectrum, okay? But the Wilson loop, also has eigenstates, for example. So this guy is not only eigenvalues, but also has eigenstates. And from the eigenstates, so if you give me the full Wilson loop, from the eigenstates, I would be able to tell you that the eigenstates are related to each other by C to Z times T, and not by T. Okay, so I'd be able to tell you that it's not a quantum spin Hall, but it's a C to Z times T Wilson loop. Okay. Also generically, actually, this spectrum, so here, because I have extra symmetries, these are at 0 and pi, but if I just keep C to Z times T, okay, generically the spectrum can look like this. Okay. So generically, with just C to Z times T, with no other spatial symmetries, okay, the spectrum can, and this is continuous here, right? Okay, and this is a twofold degeneracy here too. So C to Z times T keeps these degeneracies in the Wilson loop spectrum, okay, it keeps them locally stable, okay, but you can move them around, right? You can move them around, whereas with time reversal, with a quantum spin Hall state, you cannot. Well, not that you cannot, but these are always degenerate at pi and 0, okay? So with C to Z times T, you can move these degeneracies away. Here they're at pi and 0 because of crystalline symmetries for this sample. If you kill the crystalline symmetries, you can move it. So in the generic case of C to Z times T by itself, I would be able to tell you that this is not a quantum spin Hall state because it doesn't have degeneracies at K. If I keep spatial symmetries and get the degeneracy is pinned in the Wilson loop at 0, at k equals 0 and pi, then I will still be able to tell you that it's topological by looking at the eigenstates of the Wilson loop.
There is another question.
One dimension finite. Well, I mean, I was considering a system with 2 dimensions, but the edge state not being a circle, okay? If the edge state is not a circle, it's a rhombohedron, or like it's, if the edge state does this, okay? The edge state does this. So sorry, I should read the question. You said C2ZT acts on the edge states by exchanging 2 edge states. I guess you are considering system with only 1 dimension finite. What happens if we take a system which is finite in 2 dimensions, so the edge might map into itself on a C2ZT? So the edge doesn't map into itself on the C2ZT. That's, I mean, it's, well, depends. It's an issue of language. Okay, what we can say is that, you know, the edge, this point on the edge with C2Z times T never maps to itself. Okay, it maps to, for example, this point. Okay, and that's true no matter what dimension, what, you know, what shape or form the edge states have. So that means that locally you don't have a symmetry that to protect your edge states here. Okay, like in quantum spin Hall, you have time reversal, which protects edge states here, but locally you don't have. It means that the mass on this edge, I can open the gap on this edge. So say if I start off with gapless edge states, I can open a gap while maintaining C2Z symmetry